I mean, everyone else in the world calls that sport football, except you.
Makes sense. Football, like, in America.
Yeah.
What are we supposed to call it? Oval ball?
Handball is a different sport.
Yeah.
We call it egg ball.
It should be.
Running with the ball.
It should be called rugby, right? It is
American
rugby. It's American rugby. Yeah.
American rugby is way different than regular rugby, though.
Well,
Yeah.
I know.
Okay. Let's let's talk about the topic. Okay. Nice. So I'm assuming all of you have already submitted your exam. If not, then I mean you have already received a 0 grade on Blackboard. No, that's seriously. If you haven't participated in the exam, you will get a 0, right? And we will talk about expansion waves today. We talked about them a little bit, not that much. We will also talk about the Rayleigh flow and also the Fano flow. There will be one section of the Fano flow that is going to we are going to cover on Wednesday. Okay, and then we'll be done with chapter 2 of this book, which means that we have already covered 4 chapters of the book, and we will move on to chapter 3 and chapter 4. Okay. So, expansion waves. The idea is expansion waves. Can anyone explain to me what expansion waves are? We talked about them a little bit, right?
Where like flows going over a surface and it's like a drop down to the.
You have to speak up.
Or like the flow is going over a surface and it's going to drop down to the surface, so it expands.
So something like this. So essentially, you will get this region of Mach waves in which you will get incremental changes. Upcoming flow, maybe supersonic or subsonic, doesn't really matter. And then it will turn. So the main function of expansion waves is to turn the supersonic flows. This is the main function of expansion waves. And during this turning, the static pressure will drop. What does this mean for velocity when the static pressure drops?
increase velocity increase.
The velocity increases, increasing Mach number. So these are actually, these work in reverse of shock waves. Expansion waves are isentropic. Mainly because they are a combination of infinitesimally small Mach waves, and Mach waves are reversible, and there is no heat addition added to this, so isentropic is adiabatic reversible. But let's try to get an idea of how to calculate the flow properties after an expansion wave. Let's say you have this Mach wave, just one of the Mach waves of the expansion wave. And you have flow coming in with velocity v. What is going to happen to this flow after it has passed through the Mach wave? Its velocity is going to change. A small increment, but it's going to change anyways, right? Also, its direction, because the Mach wave is not a straight line, it's not normal to the flow, its direction is going to change as well. Let's call this change in angle d theta, right? What we want to do right now is to find the relationship between this Mach wave, this flow after the Mach wave, and the flow before the Mach wave. So, find the relationship between 2 and 1, downstream and upstream. Okay, how can we do this? How can we find this relationship?
When you say it's opposite to a shock wave, can you use the normal shock table backwards? Like is M2 instead going to be like you get M2 and it goes to M1, and that's your second.
So our solution it is actually, that's a very interesting question, and we usually use actually the expansion wave tables for the oblique shock waves. The reason is, and you're going to see this from the solution, is that we are going to have fewer assumptions when we are developing the solution for expansion waves. So the solutions we have for expansion waves are going to be a little more general and a little applicable to a wider range, right? So we can use the, but there is a limit to it as well. But we'll talk about them a little bit, just a little. Okay, so let's see how we can find the relationship between this velocity downstream the Mach wave and this velocity upstream the Mach wave. The first thing you want to do is to find the Mach angle, which is going to be this angle, mu before, and the Mach angle after. And we can do this line, right? It should actually be this line. My drawing is not that good. Well, yeah. It's actually, yeah, let's just talk about the Mach angle before. We have the Mach angle, we have the turn angle. Just to make sure we don't get confused, let me just change this a little bit. So the theta is not the same as the Mach angle. It can be the same, but that it is not necessarily the same. I want you to help me in this. How can we find a relationship? How can we establish a relationship between these two? What was this first assumption? Then we were talking about the oblique shock waves. What was this first observation we had about the velocity and the components of that velocity? We said the velocity normal to that oblique shock wave. You wanted to say something?
I saw we had rho 1 u1 equal to rho 2 u2. So I think we could do something like that here.
We can, right? But that's one component of velocity in the normal to the shock wave, normal to the Mach wave direction, right? So that's one observation. But what is the relationship between the two components of velocity that are tangential to the shock wave? They are going to be equal, exactly. So this is going to be equal to whatever component we have over here. I wanted to use this upper thing as your book does. So let me just change these angles a little bit. But okay, this is better. And then, yeah, we can use this. So these two W's, the tangential components, are equal. Okay? I want to find the geometric relationship between V and V plus dV. Just think about it. What kind of a geometric relationship we can find? And this, I'm sorry about this. This is the Mach angle. What is the angle here?
Same as
It's going to be mu, right? and this is 90 degrees. So what is the angle here? Pi over 2 minus mu, right? What's that?
I thought to use a trig identity.
Pardon me?
So could we use trig to do it, I guess? Like, that's way
Guys, we want to use trig relationships, right? What did I say? What is it?
I don't know if this is going to be useless or not, but can we make the mu and delta t equals to pi? And
Mu delta t
no, that
d theta
yes, d theta, yeah, sorry.
equals mu multiplied by d theta equals to.
So on a parallel is 180 degrees. So that angle and that angle sums up to 90. So we're gonna find the missing angle, and that's gonna give us the relationship, maybe.
I'm not sure I follow what you said.
Oh, he's saying the is that what you're talking about? That angle?
Just saying that pi over 2
Yeah.
minus mu equals d
Because you
theta.
have mu and mod over
Are you talking about this angle?
No, the
This
other
is-
one.
Pi over 2 minus mu equals d theta.
Pi over 2 minus, no. How did you make that conclusion? They are not, those two lines are not parallel, are they? So you can't make that conclusion. But what we can do is find this angle. This angle is going to be pi minus pi over 2 minus mu, right? Yes.
I was going to say, can we do cosine mu over v equals cosine d theta over v?
We can use the law of sines, right? Or cosines. I mean, we can do, that's what I wanted to get to. So to use the law of sines, we want to use the law of sines. We have to find these angles, right? This angle, when this is pi minus pi over 2 minus mu, then this plus this have to be pi, right? So we can find this angle to be pi over 2 minus d theta. Yes, minus d theta minus mu. Okay, so for this, the law of sines is going to tell us that v plus dv is going to be equal to sine of pi over 2 minus mu equals to v divided by sine of pi over 2 minus mu minus d theta. Okay, d theta, this is d theta. I think we have to decrease the Is this clear? So in this relationship, we haven't made any assumptions. It's just a trig relationship, right? And we can move all of the v's to one side and all of the sines to the other side. So let's do this. We are going to get 1 plus dv divided by v equals to sine of pi over 2 minus mu divided by sine of pi over 2 minus mu d theta. Okay? Again, the goal here is to find the relationship between the two velocities, or find the change in velocity, right, after a Mach wave. Which, if we have the Mach angle and we have the changes, the tan angle, d theta, right, we essentially have already found that relationship. We can simplify this with this cosine relationship. Is going to be cosine of mu, right, divided by cosine of mu plus d theta, again from your trig relationships. And I'm going to just write this down. This is going to be equals to cosine of mu minus d theta sine of mu multiplied by sine of mu, which is equal to 1 divided by 1 minus d theta tangent of mu. So, as long as you have the Mach angle and the turn angle, you can find the velocity after, and also the velocity. You can find the velocity after the Mach angle, right? The Mach wave. And what were the assumptions we made here? Essentially nothing, right? Except for the isentropic Mach wave, right? That was the only assumption, which is a pretty good assumption. We can simplify this further. We have this relationship for small angles that tells us, or small values. If you have 1 over 1 plus minus of an epsilon, which is a very small value, this can be replaced with 1 minus plus epsilon, which means that we can actually replace this with 1 plus d theta tangent of mu. Okay. Do you have any questions?
What's considered a small angle here?
A small value, not a small angle. It's a small value. This a small value.
So is it always going to be plus d theta tan mu, or is it going to be 1 minus?
Should what? This, if you have 1 divided by 1 minus epsilon, which is a value that is, let's say 1 divided by 0.9, right? What is this? It's 10 divided by 9, right? This is larger than 1, right? So the idea here is that if you have 1 minus 0.1, your epsilon, the solution is going to be very close to 1 plus 0.1, right? So 1.1. Is this clear? And 0.1 is a very large value for this, but you get the idea. Okay, let's see how can we simplify this further. Let's have another look at this Mach wave. Just recall the B-pair idea. Let's say this is your Mach wave, and this is your velocity vector. This is going to be your sound wave, right? The sine wave velocity, because this is going to be normal to the Mach wave, right? That was the idea. If you divide all of this by the speed of sound, you're going to get a Mach vector and also a 1 vector, unity vector, right? Or a 1, just a 1. And this is going to be your Mach angle, right? And what is this value here? This value here, let's call this a star. A star is equals to 1 plus m squared, like 1 squared plus m squared. So a star is equals to, I'm sorry, not Pythagorean theorem, right? M squared is equals to a star squared plus 1 squared, right? So this star value is equals to a square root of m squared minus 1, right? So how can we find this tangent of Mach angle? How can we find the tangent of this Mach angle? 1 over square root of m squared minus 1. Is this true? Yes? Okay. So 1 plus dv divided by v is equals to 1 plus d theta 1 divided square root of m squared minus 1. Right? These ones will cancel out. You can move the m squared to the other side. So the theta is going to be equal to the square root of m squared minus 1 dv divided by v. Again here, the goal is to find a relationship between the downstream and the upstream. So eventually we are going to use a table, right? But I wanted to go over at least one derivations when it comes to this. Any questions so far?
Did we run out of letters already?
Did we run letters?
Did we run out of letters already? We're even started.
No, I I didn't want to introduce a new confusion to you guys because we already have a lot of letters. That's why I said a star. But we want to convert this to Mach as well, right? Because we usually work with Mach number, right? We want to find a relationship between the turn angle, which is on a geometry is going to be this. And this is not the theta anymore, it's going to be theta. And also the Mach number. And using this relationship, we can find the Mach number after expansion wave or expansion fan. This is also called the expansion fan, right? Are we all following? Yes? Okay, so let's continue. How can I replace this velocity with Mach number? What is the relationship? But what can I do for this derivative? The speed of sound changes, right? It's also a function of something else. Temperature, right? So Mach number is actually, or let's do it the other way around. Velocity is Mach number multiplied by the speed of sound, right? Which itself is a constant multiplied by Mach number multiplied by temperature, square root of temperature. So derivative of velocity, how can I find the derivative of velocity here?
The constant over 2 times Mach number times temperature, and then be in the denominator.
But both Mach number and temperature are changing, right? Are variables.
And you need a partial.
You need to do a partial there. So it's going to be C dm t square root, right? Plus C again m dt square root, which is going to be about 1/2 of dt, right? Or whatever. dt to the power negative 1/2. Okay. So eventually you can rewrite dv by velocity as dm divided by m plus 1/2 of dt divided by t, which is going to be equal to the theta, right? And if you multiply this, if you multiply this whole thing by what was this? The square root of m1 squared minus 1 is going to be equal to d theta. So this is the equation we have so far. But we already have a relationship between t and Mach number, it's a constant multiplied by 1 plus gamma minus 1 divided by 2. This is for an ideal gas, right? So this is the first assumption that we are introducing here, which means that we can replace dt by t by a function of Mach number. Eventually, this is what you're going to get. dt is going to be equal to square root of m squared minus 1 divided by 1 plus gamma minus 1m squared dm. So, if you know the turning angle of that one Mach wave, that's d theta, you should be able to find the Mach number, the incremental change in the Mach number after that one Mach wave using this equation. Is it clear? Yes? Okay. But the idea is expansion waves are a combination of millions of Mach waves.
Professor, can you scroll just a little bit? That's good.
So how can I find the properties, flow properties, after these millions of Mach waves combined together? Average. So we have one opinion that we have to take an average. And is there any other opinion, or did you agree with this? Take an average of what?
Just reasonable angle.
Integration, I think, is going to be the better thing, because you are going to sum up. Let's say this is the flow coming up. This is going to turn the flow this much, 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 until it has turned completely, right? So you want to add all of these changes. Since this is a continuous thing that is happening, we cannot do a summation. We have to do an integration, right? So the integral of 0 to nu of m, this is what it's called. The other limit of the integral is called nu of m. And we are going to talk about this. It's going to be equal to the integral of from 1 to m a square root of m squared minus 1 divided by 1 plus gamma minus 1m squared dm divided by m. And eventually, if you do the integration, you will get to this function, nu of m. This is the Greek letter nu. Nu of m is equals to the square root of gamma plus 1 divided by gamma minus 1 tangent inverse of the square root of gamma minus 1 divided by gamma plus 1 m squared minus 1 minus tangent inverse of m squared minus 1. This is the function of the expansion fans. And this is called the Prandtl Meyer function. And this new parameter is called the Prandtl Meyer angle.
Is that the Mach or the angle?
Pardon me?
Is that the Mach number?
This is the Mach number, yeah. Okay, so based on the limits of this integral, go from 0 to 1, 1 to Mach number, and 0 to nu of m. What do you think this angle, the Prandtl-Meyer angle, represents? Think about it. Look at the limits of integral. So for Prandtl-Meyer angle 0, you're getting a Mach number 1, right? And for an unknown Prandtl-Meyer, you're getting an unknown Mach number, which is probably supersonic, right? Because that's what happens with expansion wave. You are going to increase the velocity or the Mach number, right? So what do you think this Prandtl-Meyer angle represents?
So like how far the body, or like the angle between neutral and the body?
It is, so this Prandtl-Meyer angle is not a real angle, right? But every Mach number has a Prandtl-Meyer angle attached to it. And we're going to see how does it relate to the real geometric angle, right? Later, yes?
Is it the maximum possible angle that the flow can bend around, like through the expansion fan?
You're getting warmer.
Does it predict the maximum Mach angle or maximum Mach value?
Maximum Mach value for a specific nu, right? Getting warmer as well.
Maximum turning angle at which that breaks the sound barrier, or not the sound, but like it goes supersonic.
You're very close. Is there anyone else who wants to like wrap this up and give a final correct answer? Any takers? No? So this essentially, this Prandtl-Meyer angle is the angle you need to have on your body, right, to turn a sonic flow to a specific supersonic flow, right? So if I go from 1 to 1.6, the angle I'm going to calculate, this Prandtl-Meyer angle, that is going to give me that angle that is needed on your shape to turn the sonic flow to Mach number 1.6. Why is it not in general representative of your body's angle, right? Why is it not representative of that specific angle? Theta here, theta of wall. Because not all of the incoming flows are sonic flows. If it was a sonic flow, then yeah, this would have been equal to nu. So which also means that for sonic flows, this Prandtl-Meyer angle, nu of a sonic flow, is 0, right? That's by definition. Does this make sense? Is it clear? Okay.
The equation for the Prandtl-Meyer angle, is that supposed to be square root of gamma plus 1 over gamma minus 1 times the difference of the two?
No, it's times this one.
Times that one specifically?
Yeah. Okay. So what if your incoming flow is not a sonic flow?
Can you have supersonic?
Yeah. And you can also have subsonic, huh?
So just not one.
Not just one, not one, yeah. Not sonic, which means that your Prandtl-Meyer angle is non-zero, right? You already have this angle, theta of wall, right? What you do is, you find the Prandtl-Meyer angle, you find it, I'm going to call it nu from now on. Nu of this Mach number, which means that you are finding the nu which is needed to turn a sonic flow to this velocity, whatever that is, right? And then you find the nu of this Mach angle, right? also whatever that is. This, which is the angle, the wall angle needed to turn a sonic flow to this speed, right? This theta of wall has to be equal to nu of m1 minus nu of m2. I'm sorry, nu of m2, because that is a higher nu. Nu of m2 minus nu of m1. So if you are given a theta of wall, you can calculate nu of m1 because it's an incoming flow, it's an upstream. You already have that value. You should be able to find the nu of m2. And using this nu of m2, you can go back to this equation and calculate the Mach number after the expansion fan.
Are you limited up to 90, or can it like invert?
It can invert, yeah, it can go back here. And you are not limited to 90, no. You are limited to 180 though. I mean, the maximum you're gonna get is 130 degrees though, the mathematical limit. For an infinite margin, we can put infinity here. If you put infinity, you are gonna get 130 degrees.
So 130?
30, yeah, close to that. Not exactly 100, close to 130. Okay, so, and you just have to keep in mind that the Mach angle itself for the incoming flow for this first Mach wave is equals to inverse sine of 1 divided by m1. Mach angle for the outgoing flow, for the downstream flow, is inverse sine of 1 divided by m2. And then we also have this theta of wall relationship, which is going to be equals to nu 2, nu 1. These are the three main relationships you are going to use. But are we going to use this equation, this long equation? Probably not. That's true. Yeah, we are not going to use this equation. What are we going to do? What we are going to do is we are going to use the Prandtl Meyer tables. Prandtl Meyer function marker. So what you see here is that you are either given a mu or a nu or an m. I mean both of them, right? This and that. Or one of them should be fine. And then you can find the Mach angle and nu for that specific case. You have the geometric angle, theta, then you find the nu for the other downstream flow. Then you find the velocity and also the Mach angle after the expansion fan. Is it clear? You can also apply this analysis to oblique shock waves, but under one condition. It will give you oblique shock waves very close to the walls are actually reverse expansion waves, right? So if you go further from the wall, you won't be able to use this expansion wave analysis, expansion fan analysis, okay? On one hand. We also have the temperature relationships between T1 and T2 is going to be equal to 1 plus gamma minus 1 divided by 1 plus gamma minus 1 divided by 2 and 1 squared. And the pressure relationship is going to be 1 plus gamma minus 1 divided by 2. This is for isentropic, of course. This is M2, right? M1 squared, M2 squared to the power gamma minus gamma 1 divided by gamma minus 1. Are we ever going to use these relationships though? I had 2 nodes, 3 nodes. How can I find the pressure and temperature after an expansion fan then?
Table.
Which table?
Normal shock.
Why normal shock tables?
So the behavior same.
Normal shock tables are going to give you the properties of the upstream based on the downstream Mach number, right? But we want to find the properties. It's very important, guys. Keep this in mind. We want to find here we already have a Mach number, right? M2, based on the calculations, based on the Prandtl Meyer function, right? We already have the Mach number after this. So we want to find the tables. We want to find the sonic tables, whatever they call. Don't remember what exactly they were called. The isentropic tables. The isentropic tables, right? So for a specific Mach number, it will give you these ratios, right? But if you didn't have the total stagnation properties at one point, at the second value, you have to come back and use this equation, these equations. Okay?
If you didn't have what?
Look at these properties is either the ratio to the sonic properties or the total properties, right? If you don't have the total properties after the expansion fan, you have to use the equation. And those equations are not that big equations, so you should be able to use them. Is there any questions so far? No. It is 7 minutes past 3. Let's do a 3-minute break, 2-minute break. Because I see some of you are falling asleep already. I didn't know I'm this boring.
We just need to see an example.
What's that?
I'm having trouble piecing it together. I just need to see an example.
Yeah, I mean, but you always fall asleep in this class. Not you, I mean, you guys.
It's about that time just after lunch.
That's probably true. I probably need to go back to using the board, huh?
For what?
Blackboard
Oh,
instead of a tablet.
I don't know if that's.
It's not gonna change anything. It's not gonna help with the boringness.
Tactile.
What's that?
Chalkboards are nice and tactile.
Yeah, I guess. That's feedback, huh?
There's situations where we wouldn't have the sonic values or the total values. How would we know we don't have those?
You are not given those.
Okay, so like it would be specified you don't have density total or something like that.
Yeah.
Okay.
What will happen? Let me ask you this. I know you don't want to be asked a question when you were asking this, but what will happen? Think about this. What will happen to the stagnation temperature after an expansion fan?
Will drop.
I don't know. I'm asking you.
Velocity is faster.
Yeah, and pressure drops.
Pressure drops, then it's colder,
And
right?
then we get colder.
We are talking about the stagnation property here, right?
At stagnation point, it'll probably heat up because it's really high condensation of air.
How do you calculate the stagnation temperature? CPT is equals to CPT plus V squared divided by 2, right? How does this stagnation property change after a stagnation point, after an expansion fan?
Well, it's gotta get higher because velocity
Yeah,
increases.
velocity increases with it.
Now what about temperature? Doesn't the regular temperature decrease? Or
Oh, yeah.
So it'd be
look at this equation here. This is regular, the static temperature. We have a higher value on the bottom, right? On the denominator, which means that this is less than 1. So this is dropping, right? Lower temperature, higher velocity. So you can't make that conclusion just based off of velocity increasing.
Does that one not grow faster though? Velocity squared over 2?
Yeah, wouldn't that become bigger to the point where the temperature change doesn't matter?
I mean, if they were changing at the same rate, yes, that would be true. But we don't know what is the rate of change, right? And all temperature change is already related to the square of velocity. So that is already being compensated here. What do you think, Drew? I want to go, everyone. Yeah. Let's just start from Zach. That's all right. But
Starts with me.
What's the question? Then we were talking about the temperature relating it to the flow, like at the expansion.
the question is, how does this stagnation total temperature change after an expansion fan?
I think I was going to say it decreases.
Decrease. Why?
I just
The
feel
why,
because
that's what I was
it just
struggling
kind of I don't I just see it seems like it because of like what they were saying, the pressure decreases. I just don't see that. I don't know.
Let me go back a little bit. What does this stagnation temperature represent?
The temperature of the stagnation.
Yeah.
No.
It's like the
It is the temperature at stagnation point, but there is no real stagnation point, is there?
surrounding temperature plus the temperature from the knock effects. Or-
It is literally by definition the static temperature plus the kinetic energy. So the internal energy plus the kinetic energy. So what does it represent?
the total.
Total energy. That's it. Total energy of the system. Does the total energy of the system change after an expansion fan?
No.
Why not?
Generate energy.
Conservation of energy.
Yeah,
Conservation. That's true. That's true. But why the energy is conserved here? Why don't we have any losses?
It's isentropic.
Isentropic and frictionless, right? Okay.
So the temperature is the same?
Temperature is not the same. A stagnation temperature.
Stagnation.
It may remain the same. Right?
What about the temperature?
What do you think is going to happen to temperature? If this is the same and this is increasing, what is going to happen to this?
That'll have to
Decrease in order
It'll have to decrease.
And also, you couldn't actually make the same conclusion using this equation. Right?
The total temperature will increase, but the
No.
no
Total
the
temperature.
stagnation
Yeah,
temperature
stagnation.
increase.
No. Same.
A stagnation temperature and total temperature are the same.
Okay, so which one stays the stagnation?
This is a
temperature?
static temperature. This is a stagnation
Okay.
Too many SPA words.
or total.
So are the pressures and temperature ratios above static ratios or can we,
These are static ratios.
okay, but could they also be total ratios?
No,
We made them
you
both?
have to come up with a new equation. I mean, you have to come up with a new equation. But we have some of those equations. If you take the compressible fluid flow course, you will see that those equations in more detail.
So, just to be clear on the stagnation temperature, that's the static temperature plus the kinetic energy of the fluid over the surface.
That's the idea. Yeah.
Does that mean you're getting like hotter on the front and colder on the back in terms of like an airflow going through?
An expansion fan, you are not getting hotter on the front. Your temperature, a flow comes into expansion fan, and the expansion fan is going to change its properties, right? But let's stop with the questions here, and you will get to do a simulation for the expansion fans and the Rayleigh flow, all of those things, so you can actually test all of the hypotheses in lab 2.
Next year.
Yeah.
Year away.
What's that?
A semester of a year away.
Yeah, I mean,
It's like next week.
yeah, Nicholas was the one who was asking the question, so it was directed to him.
No.
Prepared for it.
Okay, if you pass lab 1, it's going to be next period. If you pass lab 1, yeah,
How hard is it? Are you gonna make lab one?
it is. Huh?
Lab 3 graded.
You have already made all zeros on quizzes, right?
Yeah.
I'm just kidding.
Yeah,
I haven't-
checking for those.
Let's keep it
Not-
going.
Yeah, you guys also. So you don't really ask about the quizzes, but let's forget about this. Let's go back to the Rayleigh flow. I wanna talk about the Rayleigh flow as well. At least Rayleigh flow. Rayleigh flow. So we have already talked about convergent divergent nozzle. Right, and we already know what's the effect of convergent divergent nozzle, or in general nozzles and diffusers on supersonic and subsonic flows. What are the effects of a nozzle, or what are the effects of a decreasing area on subsonic flow?
Increases.
It will increase, right? What about the supersonic flow? Decrease. So the same effects is going to happen with an applied heat flux. So you have a constant area duct. The duct's area is not changing. So area constant. That's the first assumption here. And we are going to assume the friction, it is a frictionless flow. The only input we have is a heat flux. Q double prime.
Q double prime.
That's a heat flux, right? Total heat divided by area. This is going to have the same effect as the change in area, meaning that it is either going to accelerate or decelerate supersonic and subsonic flow. And we will also experience choking at sonic conditions.
So heat flux can speed up airflow, like changing area can.
We will talk about how it is going to affect that. So let me actually give you the governing equations. I'm not going to go over any derivations here. We have already done enough derivations for today. You have to keep in mind that with this specific case, fluid impulse is conserved, meaning that P1 plus rho 1 U1, I mean, it's the same thing here. You can just say fluid impulse. We will talk about fluid impulse a little more in chapter 3.
Is that P2 as in pressure minus rho?
No, this is P.
Equals P1 minus P2.
This is rho 2, rho 2 to rho 1 U1 minus P1 equals to P1 minus P2. So whenever you are dealing with the momentum equation, usually on the left hand side you have the momentum terms, which is rho U. On the right hand side you have the force terms. In most of our analysis we are going to use only the pressure force. Okay? I don't know how to cover this in 15 minutes. That's the hard part, isn't it? Okay. So let's actually do a general introduction to this, and then we'll come back to the equations next week. We can actually find a relationship between the changes in entropy in a Rayleigh flow and the Mach number and also the temperature using the Gibbs equations and all of the things that we have seen in our course so far. And we can have a TS diagram. How can we get the maximum value of temperature here? You can get the maximum value of temperature when your ds is 0. And the maximum value of enthalpy is going to happen when your when your m is 1. That will be the maximum value of enthalpy. So if you want to plot this relationship, this is what you are going to get. This is going to represent the maximum value of, not enthalpy, entropy, which is going to be the sonic condition, m equals to 1, or the star condition, right? And then this is going to be the maximum value of temperature, where dt divided by ds is 0, right? Because it's just this line. I'm sorry. Let's say you have a subsonic flow. A subsonic flow is going to, at a specific condition, temperature. A subsonic flow is going to fall on this line. So this part of the curve, is going to be the subsonic part of it. And this part of it is going to be supersonic part of it. If you heat your system, you are going to cause an acceleration. So subsonic flow, subsonic heating. And what I mean by this is that heating is subsonic flow. Subsonic heating as a concept does not exist, right? Doesn't mean anything. Heating a subsonic flow will cause an acceleration, which means that you are going to move towards this sonic condition, at which you will experience choking.
What is going to cause accelerating? Is it going to create the pressure difference kind of thing? Like why it accelerates?
Think about it yourself. What happens when you are heating air?
You're adding energy.
You're adding energy to it, right?
Yeah.
Right? So your total energy is going to increase, which essentially means that your total energy is a combination of your kinetic energy as well as temperature. It will increase both of them, right? That's the idea. And if you cool it down, it will cause a deceleration. But it will, and we will see you will understand this from the equations a little better. I didn't want to go through the equations here, because we have a very long list of equations, and I think you are already exhausted with equations. So I just wanted to give you the concepts.
I don't know if it's because of recovery, but thinking about a pressure cooker helps sometimes.
What's that?
Thinking about a pressure cooker helps sometimes.
Pressure cooker. Okay. I guess. And this other line is going to represent the supersonic flow. So we are going to have the reverse effect on a supersonic flow, right? By heating, yes.
So, just what region of that curve is subsonic? What region is supersonic?
This region,
Left
At the
is
sonic point.
this region is subsonic.
Uh-huh.
This region is supersonic.
Okay, that's what I thought.
It is going to decelerate when you are in the supersonic region, right? So that's the idea of that. In general, that this is the idea of Rayleigh flow.
Wait, so when you increase the temperature or the heat, you're decreasing it at a subsonic when you're over some.
You remember the equations we had that related the area, the change in area, to the Mach number. You remember that part? And based on that equation, you could clearly see that an increase in area is going to decrease or decrease the Mach number in a supersonic condition, because we had 1 minus m squared. You remember that? It was 1 minus m squared dm divided by dm is equals to dA divided by dA, right? You remember this? So for a subsonic flow, or m squared minus 1, I'm sorry. That should be. For a subsonic flow, this would be negative, which means that this will act in reverse directions. For a supersonic flow, this will be positive, which means that they are going to act in the same direction. For a Rayleigh flow, we are going to get the same equation, which we are going to see next Wednesday, on Wednesday, right? The same type of equation. And you could clearly see that by increasing and by heating this up in a supersonic region, you are going to decelerate, and by heating the flow up in a subsonic region, you are going to accelerate.
Because it just seems like you're adding energy, like you were.
We will discuss the base. You will see this, right? We will see this.
What's the temperature scale we're looking at here? Like, is this something we'll see in flying over a desert versus flying over a...
It doesn't have. There is no scale to it. It really depends on the inlet conditions. So that heating is the big part of it. You can be in a sub-zero condition and you start heating your flow. You will see the same effect. I mean, it has to be compressible flow though, right? So you have to be in compressible speeds. Okay. But let's actually, since we have already talked about the basics of the Rayleigh flow, let's talk about the basics of the Fano flow, and then we'll go into details and we'll solve examples on Wednesday. A Fano flow. So far we have seen the effects of change in area and also applying a heat flux or removing heat using a method. And we have seen the effects of it on your flow, right? The next thing we want to discuss is how friction is going to affect your flow. We have three main mechanisms to accelerate or decelerate flows in subsonic and supersonic regions. We have discussed one much earlier. We just discussed the heat flux, and the third one is friction. So moving, if a subsonic flow, a compressible subsonic flow is moving inside a duct, we will definitely have friction. And it will affect the velocity. It will either accelerate the flow or decelerate the flow. The same effects, right? So that friction effect is going to be called flow with friction, with a friction dominance, is going to be called the Fano flow. We will go over these two in a little more detail on Wednesday, and I will solve two examples. The Fano flow part, solving Fano flow problems is a little time consuming and may get a little confusing, because you have to find the location of a shock wave inside the tube, right? And that's something that needs trial and error, right? So it may get confusing a little bit. Just be prepared on Wednesday. Make sure not to eat greasy food. You are conscious, so you are conscious in class. You are not asleep in class.
There's no equation equation to find where the shock wave is gonna act in the tube? You have to like guess, and then.
There's no equation, and that's a very good question actually. There's no equation. The reason is that the flow at the outlet, we need to have a specific condition, right? Meaning that the inlet is going to adjust based on the length of the tube, right? So you can actually write the code and do all of this trial and error for yourself, but there is no specific equation that is going to spit out a specific number for you. Any questions?
Professor, when do you think those exams will be graded?
The exams, I actually looked at the